Hey there, everyone, and welcome to your next lesson on further maths algebra. Today we're looking at the binomial theorem. So, not a particularly big topic for today. Let's take a look at the lesson plan. We just have these two sections. First, we're going to look at Pascal's triangle, which is something you'll be using a lot of. It's a pattern of numbers that we can use to expand out. Um, Brackets when we have many brackets multiplying each other, but only under certain circumstances, which we'll see in a minute. And then the binomial theorem is a way of, essentially taking this and formalizing it into, well, a formula that is really handy under certain circumstances. Like, say, if we have very high powers that we're dealing with, or maybe we just want a specific term to calculate as opposed to calculating out of, every term in the expansion. So here we go. Let's make a start on this. So first of all, Pascal's triangle. What is this? So um, what we're trying to do is we want to expand something like this, where we've essentially got two terms. At the moment, we're just keeping it simple, x and y. How do we expand out these two terms raised to some power like this? That is the question that we're ultimately trying to answer here. Um, the first way we can do this, a simpler case, yeah, is using what we call Pascal's triangle. Um, and what this is, well, let's build this up by first of all starting off with expansions that you're already very familiar with. So let's take the simplest case where say if n equals 1. So, well, n first of all, n is integer. We're not dealing with like fractional values. We're just talking about positive integer values, 1, 2, 3, 4, so on. So first of all, 1, what is this? Well, that's just going to be x plus y, isn't it? Then the next one, x plus y squared. What is that going to be? Well, we know how to expand that, don't we? If you expand and collect together like terms, you're essentially going to get this. Now, x plus y cubed. How would we do this? So we basically take the previous expression, times it by x plus y again. We've already seen, how you could do this anyway in the previous lesson. And if you do that and collect together your like terms, you'll find you'll get this. And you might already start to see a bit of a pattern going on, but I've got a feeling this might break it. Say if we do x plus y to the 4. So again, you could take the previous one and multiply by x plus y again and collect together your like terms. And what you'll get is this. So what we want to try and do here is spot a pattern that will allow us to expand this out very quickly. Like say if I wanted to do x plus y to the power of 10 or something, how would I do that without having to work out all the ones before, 1 through 9? Um, and what when you do is pay close attention to those coefficients. So if you look in the first one, x plus y, the coefficient is just 1, 1. The next one down, it goes 1, 2, 1, doesn't it? The next one down, it goes 1, 3, 3, 1. And then the next one, it goes 1, 4, 6, 4, 1. So what we'll do is we're going to put this as like a pyramid like this, or a triangle, I should say. This is going to be the beginnings of our Pascal triangle. And you see this is basically for n equals 1, 2, 3, and 4. There is also the trivial case of when n equals 0. If you do to the power 0, you're just going to get a 1, don't you? So that's just 1 at the top of the pyramid, or I keep saying pyramid, triangle. Pascal's triangle. So this is a pattern in the in these coefficients that there's this famous mathematician known as Pascal who found this. And if you look closely at those numbers, you might be able to notice a pattern between each row and the previous row. So you might want to pause here and see if you can see what that pattern is. If you look at each row and compare it to the row above it, if you've spotted the pattern, well done. If not, you might notice that each number is basically the sum of the two numbers above it. So if you look at those threes, you see above it, there's a 1 and a 2. Or you look at, say, the 6, the two numbers above it are 3 and 3, which add to produce 6. The two numbers above the 4 is 1 and 3, so it adds to get 4. And we can follow that pattern on, so without even having to expand out the next, um, you know, expression in this sequence, x plus y to the power of 5, we can work out that the coefficients are going to be this. So you're always going to have 1 on the outside. The next number along is 1 plus 4, which is 5. The next number along will be 4 plus 6, which is 10. And then you'll find it will repeat. It will be like this whole thing is symmetric because you're then going to get 6 plus 4, which is also 10, and then 4 plus 1, which is 5. So you see it's always symmetrical. So yeah, using that, you might want to pause here and see if you can work out the next row for n equals 6. And if you've given that a go, you will see it will be this. Just adding each of the two numbers, each pair of numbers as we go along, you can then get the numbers for the next row down. And this continues on for forever, really. You could calculate the coefficients of x plus y to the power of whatever number. And so now, say if we wanted to find x plus y to the 7, could we work that out without having to actually, expand out all those 7 brackets? Well, yeah. So first things to notice is the pattern with the x's and the y's. So the first term and the second term. Notice with each one, the first term, the x starts at the maximum power and gradually works its way down. So say if we look at x plus y to the power 4, the first term is x to the 4. The next term has x to the 3. The next term has x to the 2, and so on, until x disappears entirely in the last term. With the y, the second term is the other way round. It's absent from the first term, and then you get a y in the second term, a y squared in the third, a y cubed in the fourth, and so on. So first of all, we're going to have this pattern like this, where we're going to start off with x to the 7, 6, 5, 4, 3, 2, 1, all the way down. And with the y, you're going to start off with no y, and then you have y, then y squared, then y cubed, then y to the 4. It's always going to follow that pattern. And then the additional coefficients we may get, or not may get, that we will get, will basically correspond to the 7th row of the, or I should say the 8th row, because it starts from 0, doesn't it? Of Pascal's triangle, which we don't have there yet. You take a look at that now and see if you can work out what those coefficients are. And if you've done that, you should see it will be these values. Because 1 plus 6 gets us 7, 6 plus 15 gets 21, 15 plus 20 equals 35, and so on. It's then symmetrical, isn't it, on the other side? Now, it's not always going to be symmetrical. It is in this case. Pascal's triangle is also always symmetrical, but in terms of your expansion, it may not always be. It depends what those two terms are. At the moment, we've just got an x and a y. But so, Pascal's triangle, binomial theorem, it's all about patterns. So you see there's this pattern of the x's going, like the first term going down in powers, the second term going up in powers, and then these additional coefficients that come from Pascal's triangle, which is, essentially how many different ways we can make each term. That will be important later. Like say when we look at x plus y squared, you see we get a 2xy in the middle because we get an x times y and we get a y times x, and that comes together into essentially two combinations, an xy and a yx. That'll be important later. So let's put that up in the corner so we can keep note of that, because we'll need that for some of the problems we're working on. Let's take a look at this one first of all. So okay, we haven't just got a simple x and a y now. We've got two terms, that make up a little linear expression, 2x plus 3. And so that's why when we were talking about the x's and the y's a moment ago, I was talking about more in terms of the first term and the second term, because that's the more the way you want to think about it. So if we wanted to expand this out, how would we do that? Well, let's follow the pattern that always happens. So you're going to get the first term to the power 5, 4, 3, 2, 1 as we go across each of the terms. And then it'll be gone in the last term. And the 3 won't be in the first term, but then in the next term it'll be 3 squared, 3 cubed, 3 to the 4, and then 3 to 5 in the last term. So that's the pattern we're going to get, and you'll see it will look like this. Notice how I've put the 2x in brackets because it's the whole thing being taken to the power, not just the x, but the 2 as well. So that's an important thing to note there. The whole first term is being raised to those powers. So yeah, so we're just following that pattern of the first term and the second term going, up and down in powers respectively. And then the coefficients correspond to the appropriate row of Pascal's triangle, which we can see are going to be 1, 5, 10, 10, 5, 1. And I haven't put in the ones because times it by 1 doesn't make a difference, does it? So now we've got our full expression, the full expansion. The beautiful thing about this is there's no need to collect together like terms or anything because that's already been done for us essentially, following this pattern. We just need to essentially expand out each individual term. So 2x to the power 5 will be 32x to the 5. 5 times 2x to the 4 times 3 will get 240 times x to the 4. So you just got to collect together the number part and then the variable part. And you go all the way down. You could check all these numbers for yourself. 3 to the power 5 at the end is just simply going to be 243. And we get this full, what we would call a quintic polynomial, because it has a power of 5 there. So, that's what we call a quintic polynomial, if you're interested. So there we go. That's an application of using, Pascal's triangle there to expand that out without having to actually do 2x plus 3 times 2x plus 3 times 2x plus 3, over and over again. We can do it quite quickly there by observing these patterns. So let's look at another example here. Another thing to be wary of here is when you have minus signs. We need to be very careful. So now that we've had a bit of practice with this, you might want to try and give this one a go yourself. So yeah, if you want to pause here and give this a go yourself first, yeah, please do so. Um, and yeah, if you've done that, hopefully you'll get the same as what I'm about to get. So remember, got to follow the same pattern. We're going to get the first term going gradually down in powers, the second term gradually going up in powers, but notice that second term has a negative sign. And we learned in the previous lesson that that affects it, doesn't it? Because negatives respond to powers differently depending on what the power is. So we're going to essentially get this. So we haven't actually computed the powers yet, so we don't have to worry about it right now. But you make sure you use your appropriate brackets. It's the whole thing, the -3 and the x are what again raised to each power. And you see we're going from power of 4 down to 0 or 0 up to 4 in each case. And we've got to put in the appropriate coefficients from Pascal's triangle. You see we're going to get 1, 4, 6, 4, 1. And there we go. That will give us our completed polynomial here. And we just need to simplify this now. And this is where we need to be careful of those minus signs. So you see the signs of the terms are going to alternate, positive, negative, positive, negative. Yeah. And it's just a matter of calculating those out. So 4 times 5 cubed times -3 gets you -1500, for example. And then the x is just going to be x, because you see that's not being raised to the power 3 there. It's just x in that particular term. And you just got to go for each term individually. So that's it really for Pascal's triangle. Pascal's triangle is good for ones like this where the powers aren't too big. But you could imagine if we had, say, something like n to the power 20, we wouldn't want to go all the way down that pyramid to n equals 20, which we would kind of have to do because each row is calculated from the row before. So we would have to calculate all the rows up to 20. And we don't want to do that. So is there a faster way we can do it? Can we maybe just calculate it for n equals 20 and not have to do all the ones before? Well, this is where something known as the binomial theorem comes into play, which is basically the same thing that we've just done, but we've formalized it a little bit more, into a formula. So go back to our original question. This is what we're trying to do, where we've got two terms. We go back to just a simple x and a y again. Two terms that are being added, raised to some power, some integer power. What is that going to look like in the general case? Well, it's going to look like this. So, right, this might look a bit complicated, but let me explain this formula. So, this is basically saying the same thing that we've already done. So if we look at the x's and the y's first of all, what is basically saying is we start with the maximum power of x and we gradually go down. We start with the minimum power of y and go up. Um, so in case you haven't seen this summation symbol before, that's that big, kind of E looking shape where we've got k equals 0 up to n. You probably would have seen this a little bit more if you've looked at series, but some of you might not have seen this. What this is basically saying we want to sum up this expression evaluated for a bunch of different values of k. So what we do is we take this little expression that we've got, we evaluate it for k equals 0, and then k equals 1, and then k equals 2, and then k equals 3, all the way up to n, and then we sum all of them up. That's basically what that symbol means. It means sum up that expression for all those different values of k. So you see what's going on here. If we look at the first one, it's basically the power of x there is going to be x to the n, isn't it? Because k is 0. Y will be y to the power 0, and so it disappears entirely. And so you've basically just got x to the k. And then gradually as k increases, you see the power on the x is going to go down. And you see the power on the y is going to gradually go up. And so that's the same thing as what we've just seen. That pattern that goes from one term to the next. The x powers go down, the y powers go up. And then the coefficients that we add on from Pascal's triangle, that's this n choose k thing at the front, nk in brackets that looks like a vector. Well, perhaps you remember from our first lesson what that is. That's basically our combinations formula. And the reason why that is because when we expand out our brackets, you'll get each type of term. There's so many, there's different ways of combining our two terms that will produce each type of term in the answer. Like say the simplest case for when we was doing x plus y to the power 2, you see that middle term becomes 2xy because we get two versions of xy, don't we? We get xy and we get yx. There's two ways of combining x and y together, and so that's why there's that two coefficient coming up. Well, it's the same for all the others. As we go up into higher and higher powers, there's more and more ways of combining those terms together. And so the numbers get bigger, but it's the same logic. It's basically thinking how many different ways of combining things are there. So let's say if we try applying this to this formula, this expression here. So we're doing x plus y to the power 4. So we've already seen before what that looks like. But we're going to calculate it using this binomial formula here. And so, okay, we see n is equal to 4. And we're going to sum this up, all these terms for various values of k from 0 up to 4. And you're essentially going to get this. That will be the first term. So you imagine you're substituting in k equals 0, you're basically going to get this. If you then put in k equals 1, you get this. And then if you put in k equals 2, you get this. You put k equals 3, you get this. And then finally you put k equals 4, you get this. So you see, you can already see there with the x's and the y's, we've got that pattern going on. We start with x to the 4 and work our way down. And y is absent at first and then gradually goes up in powers to y to the 4. And you see those coefficients. We can calculate using this formula for the ways of choosing k things from n items, essentially. And you might remember from Pascal's triangle, these values should be 1, 4, 6, 4, 1. Well, if you try working this out using the combinations formula, you find you will get exactly those values. So it's really interesting there, an interesting application of combinations there. When, say, if you look at, for example, the x cubed y term, you see we get a coefficient of 4 because there's 4 ways you could do 3 x's and 1 y. You could do y x x x. You could do x y x x. You could do x x y x, or you could do x x x y. There's your 4 combinations, and so that's why that you see that coefficient of 4. It's a little bit more complicated to explain why this coincides with Pascal's triangle. Like, why does sum in the, each pairs of numbers um, in each row then produce the numbers in the next row? Using what you do know about this, like that each row is basically your times in the previous answer by x plus y. That's essentially what gets you to the next row. You could play around with that yourself if you wanted to, and sort of see how does that affect the coefficients. So if you took this expression that we got here, you times it by x plus y again, you're basically going to now get x plus y to the 5. And see how those coefficients change. And it might help you understand why these numbers produce Pascal's triangle there. But I won't go over that now because you don't need to know that. That'd just be more something if you're interested in. Right. So what's the use of using the binomial theorem over the Pascal's triangle? Well, let's say if we take a much bigger one like this, we've got a very big power like 15. So we don't want to compute Pascal's triangle all the way down to 15. Um, and maybe we don't even want every term. Maybe we only want the x to the power 12 term in this expansion. How would we work that out? Well, looking at this formula here, you see the first term is going to be taken to the power n minus k. The second term is taken to the power k. Well, in this case, the first term is the one that contains the x. We've got 2x there. So 2x is going to be taken to the power n minus k in each term. So, okay, we think what value of k will produce a power of 12? Well, if the power is basically n minus k, or 15 minus k in this case, because n is equal to 15, well, k must then equal to 3. When k is 3, that's going to produce a term where the first term in our expansion is the one that's being raised to the 12th power. So that's how we can work that out. And we can just find that one term. So we substitute in k equals 3. And you see, indeed, yeah, look, you see that 2x is being taken to the power 12. So we can see that's going to produce an x to the power 12. And all we need to do is expand this out. You see, we're going to get quite large numbers here because the power is very high. There's a lot of different combinations going on. But yeah, we can use that formulae. And for something like this, you would be expected to have a calculator. You wouldn't be doing this on paper, so don't worry about that. You would have a calculator. And you can see we can calculate that 12th term is going to be this. And so you see it's much simpler. We don't have to calculate a whole bunch of rows of Pascal's triangle. We don't even have to calculate other terms in this expansion. We can just calculate the one term that we actually want. Or another very common thing that we do is say if I had something like this, and what I wanted you to do is to estimate this expansion by ignoring all powers of x that are greater than 3. So we only want the powers of x up to x to the power 3. And this is a very common thing we do because say if we knew x is going to be a small number, a very small number, and like a small fraction. And we know, like remember from last lesson, when we take a fraction to a power, it makes the number smaller. Like half times a half gets smaller, doesn't it? It becomes a quarter. And if you times it by half again, and then a half again, and a half again, it's going to get smaller and smaller and smaller. And beyond a certain point, the values might be so small that they're not even worth calculating. Like this is something I've used in my work a lot. Like say if we're programming a computer to do something and we want it to run really quickly, we might take little shortcuts like that to simplify the calculation so it can run really fast and still get a very, very accurate answer, even though it won't be exact. So how we'll do that, we'll do something like this. Using the binomial theorem here, we'll expand this out, but only up to the x cubed term. So what we're doing is notice that the x is in the second place this time. You could swap it around, and instead of doing 1 plus x, you could do x plus 1. Although that's not necessary in this case because we only want the lower terms. No, sorry, that would be necessary in this term. Like rather than going from k equals 0 up to n, you might want to consider going from k equals n down to 0. Um, because you see when k is equal to n, that's when you're going to get the lowest power for the first term. So say if your x was in the first term, you might want to do it like that. So yeah, bear that in mind. You don't always have to sum from one end to the other. You could start from the other end and work your way back. But either way you need to do it, we just want the lower powers of x like this. And it's quite nice because the other term is just a 1, it's not really going to do anything. So all we've got to do is do the combinations calculation, and then we've got our powers of x, and you see you'll end up just getting this. And so this would be a great way of then estimating the value of this expansion without having to calculate 11 terms. We only have to calculate 4. So there we go. That's it really. So there's not much to um, this. You've got Pascal's triangle, which you could use most of the time, but for more nuanced cases like this, where maybe you've got quite high powers or you just want a particular term, binomial theorem can be really handy. So let me leave you with a little challenge question here. So without the use of a calculator, can you find the value of 0.9 to the power 5 by using the expansion of 1 minus x to the power n and choose an appropriate value of n and x? So give that some thought. It might not be immediately obvious what those values of n and x would need to be. Um, and yeah, see if you can use what you learned in this lesson about expansions to see if you can find the value of 0.9 to the power 5. So, that's that. Here's your takeaway for today's lesson. Top tips, checklist. Certainly make sure you've got all those points. Next time we're gonna move on to cubic equations. So we've looked at, you should already be very familiar with linear and quadratic equations. We're taking up to the next step, the next type of polynomial, which is known as a cubic equation. And we'll look over that word polynomial a bit more because I've used that a lot. You may or may not be familiar with that word. We'll be looking at that in a lot more detail next time. So yeah, I'll see you there.